All right. Did you have a good weekend? Pretty good. So.
We got out to the game.
Yeah, that's true. Seems like Kennesaw State has our number. They've done really well against us.
Also, what is our second test?
Second test. Yeah. Well, let's see. I'm gonna look at the calendar. Maybe I can tell you. I think it's looking like the 20th. I think. Let me see if that sounds right. I think that's right. Yeah. So we've got 2 sections out of chapter 6, and then 2 sections out of chapter 7, and then it'll be test time. So this week we'll get the chapter 6 stuff done. Next week we'll get chapter 7 stuff done, and then we'll have a review and be time for test. All right, so chapter 6, we're doing some geometry. I skipped 6-1. 6-1 is lines and angles, and everyday life, I don't think it's all that useful. Angles can be useful, but not to the degree that we have problems in 6-1. So let's skip over it. And in 6-2, we're going to be working with flat figures, okay, 2-dimensional figures. So we'll do some circles, some polygons. I guess that's it, just circles and polygons. Okay, and then in 6-3, we'll do some 3-dimensional stuff. So we'll do some volume and things and surface area in 6.3. Okay? So today we're dealing with the flat shapes. Okay? So some of this, maybe all of it, depends on, I guess, how good of a geometry class you had. Will be review. Okay? That's okay. Geometry is something that we deal with every day because everything that we interact with on a day-to-day basis is made out of some type of shape. Okay? So even if it's review, it's good to go over again. Okay? All right. So let's do a quick review about some of our basic shapes here. So the main ideas we're going to be looking at in this section, we're going to talk about perimeter and area. Okay? Or if you're dealing with a circle instead of perimeter, we call it circumference. So we will have circumference in here as well. And then we'll do a couple similar triangle things. That's about it in this section. So let's review a little bit of background information on some of these shapes we're going to be working with. Okay. So if we have a circle, as far as the formulas we're going to use in this section, we have 2 important dimensions of a circle. Okay, so the one that goes from the center out to a point on the circle, okay, we call the radius. Okay. The one is the radius, halfway across the circle. Okay. And then the one that goes all the way across the circle through the center, and we call the diameter. Just a quick mention on which one of those is which. Sometimes it's easy to get them mixed up, which one's which. It doesn't mention it here, but there is a name if you just draw like some line just through a random part of the circle. Okay. It has a name. It's called a chord. Just like in music. So the diameter is a special chord. And then the radius is not a chord because it doesn't go all the way across, but we got those 2. So if we are given the radius, we can multiply it by 2 to get the diameter. If we're given the diameter, we can divide by 2 to get the radius. That's the important part for us on those 2. Okay. We do have some things to mention about polygons as well before we get going with all the formulas and stuff. So a polygon is just basically any shape that has flat sides. Okay. Our definition here says it's made out of line segments, 3 or more. And if you have 2, you can't connect them. So we have to start with 3. We'll get the triangle. And if we have 4, we get a quadrilateral. 5, we'll get pentagon. 6, we get a hexagon. You may remember 7. 7's a weird one we don't talk about as much. 7's a heptagon, H-E-P. 8, you probably know. What's 8? The octagon, yeah. Any MMA fans? The octagon, or stop sign. That stop sign. And then it goes on and on. We go up to 9's nonagon, 10's decagon. If 11 has a name, I don't remember it. At a certain point, there, somewhere in there, we stop giving the different sided figures names, like special names, and we just call them something gone. Okay, so gone means side for us. So the generic name for a polygon we call it an n-gon. So like if we have something that's 15-sided, instead of having to remember a bunch of different names, we'll just call it a 15-gon. So triangle is really just a more specific name for a 3-gon. And something that you probably never thought about, but once we start with quadrilateral, it has a little bit of a different naming convention. Right, quadrilateral, and then we call them gons from there up. But even with the quadrilateral, we're naming the shapes, the polygons, by how many sides they have. But not with the triangle. So it stands out on its own. We call it a triangle. We say it has 3 angles. I don't know why that's our convention. We count the angles on the triangle and then start talking about the sides. So, triangle has 3 sides, so we could call it a trilateral or a trigon. Right? So I kind of like trigon myself. It's not going to be on the test or anything. Just something to think about. Okay, and then each one of the corners, each place we have 2 sides that meet. I call that a vertex. You have multiples of vertices. Okay. And then the other thing this slide tells us about is if we have a diagonal of a polygon. So all a diagonal is if we start at one vertex and we draw a line to another vertex that's not already connected to it. So that would be a diagonal of our quadrilateral there. Okay. And most of the polygons, most of the shapes that we're used to dealing with, in math class at least, fall into this first category of polygons we're going to look at, called convex polygons. We don't talk about it a lot for some reason when we're learning these, but the ones we're used to seeing, especially the ones we call regular, where all the sides have the same length and all the angles are the same, those are all convex polygons. And the idea of a convex polygon is that if we draw any diagonal, okay, so I could draw these 2, or I could go to a different vertex and draw the same diagonals across there. Any of the diagonals we draw in a convex polygon are going to be inside the polygon. So we get a convex polygon that way. The weirder ones, the ones we're not used to seeing, are concave polygons. Okay. So they don't behave as nicely, so I guess that's why we don't talk about them as much when we're learning about polygons. But here, these concave polygons, it's possible, like if I draw a diagonal on that one, my diagonal's outside of the polygon, right? It's not on the inside. Or I could draw one like that here. So that makes these polygons concave. You can talk about convex and concave by the angles in there as well. You can say for a convex polygon, all the angles are less than 180 degrees. For a concave polygon, we can have angles bigger than 180 degrees. The same way of thinking about the same thing. Okay, and then one little interesting note about the concave polygons is there's no such thing as a concave triangle. Okay. You can think about it, if you try to use 3 lines and connect them together, there's no way you can make one where one of the angles is greater than 180 degrees, or you can think about there's no way you can make one where if you draw a diagonal, it is outside. But 4-sided or more, we can have concave. All right. Questions on any of that stuff? All right, so with that kind of reviewing behind this, we're on our way to using some of our formulas and thinking about some of the calculations we want to make. Okay, so the first one, hey, let's think about the angles in these shapes. Okay, so you may remember if we add up all the angles inside of a triangle, anybody remember how many degrees it is? Usually one you keep in your memory. Didn't have good geometry teachers? That's okay, a lot of people don't have good geometry teachers. So, all right, so if we add up all the angles inside of a triangle, we'll get 180 degrees. Okay? That's true for every triangle, no matter what kind of shape, you know, if you stretch it out or squish it, as long as it's a triangle, if you add up all the angles in a triangle, we'll get 180 degrees. Okay? And we can think about the same thing for other polygons. So, like if we do a 4-sided quadrilateral, okay, so let's call that a quadrilateral there. Okay. Then if we add up all those angles, we're going to get 360 degrees. Okay. And the thing that's kind of happening behind the scenes there is that, if you might notice, right, it's double, right, what we had in the triangle. And so what's happening there is if you have something 4-sided, you can think about a rectangle if you want to. It doesn't have to be a rectangle, but if we have something 4-sided, we can split it into 2 triangles. So we end up with twice as many degrees on the inside. If we go up to 5-sided, we get a total of 540 degrees. And again, we've got something 5-sided, we can split that into 3 triangles. So we did 3 times the 180 and get to 540. Our goal here, okay, is just pick up on the pattern, because we want to be able to have some figure with some number of sides and be able to figure out if we add all the interior angles out, what are we going to get. So our pattern here, each time we go up, we're going up by 180 degrees. If we're thinking about it based on the number of sides we have, well, for 3-sided, we do 1 times 180. For 4-sided, we do 2 times 180. 5-sided, we do 3 times 180. So our pattern, we take the number of sides and subtract 2, and then we multiply that number by 180. Okay? So here's our little formula. That says if we want the sum of the measures of the interior angles, so if we add up all the inside angles, for an n-sided polygon, n minus 2 times 180 degrees. So we take the number of sides minus 2, multiply that by 180 degrees. So gives us just a nice little formula. We can figure out the sum of the interior angles of any kind of polygon, okay? Any convex polygon. So let's look at one. Then once you have the formula, these are easy. let's look at one. This one was not on our little table. It says, what's the sum of the measures of the interior angles of an octagon? Octagon, how many sides is that going to be? 8, yeah, so that's 8-sided. So it'll be 8, so here's our formula. So 8 minus 2 be 6. 6 times 180 degrees. What'll get there? 1080 degrees. Just plug it into the little formula. So that formula will be on the formula sheet for test 2. You didn't know how to use it. Not too bad. Questions on doing those? Okay. All right, the next little, we have a bunch of little small topics with the geometry stuff. So the next little small topic, if we're dealing with similar triangles. So the idea of similar triangles is we have triangles that are the same shape and they have the same proportions as each other, but their lengths, side lengths are different. Okay, so basically we're saying we have a big triangle and a little triangle that have the same shape. Okay. So we call those similar triangles when they're like that. Okay. Now if we had like this triangle and this triangle, they would not be similar because they're different kind of shapes, right? Even though they're both triangles, their side lengths don't correspond to each other, right? They're different. So these are not similar. Okay. So the nice thing about having similar triangles is that we can set up ratios, we can set up proportional equations. So like if we know maybe the length of this side, the vertical side of the big one and the vertical side of the small one, right, that relationship is going to be the same as the bottom side of the big one to the bottom side of the small one, or the diagonal side of the big one to the diagonal side of the small one. They're going to be proportional to each other. And we just spent some time talking about ratios, so we can use those ratio ideas and those proportional equations and figure out some stuff about our two triangles. Okay. All right, so look at one. Okay. Let's look at this one. Okay. Suppose a man who's 6 feet tall, standing 20 feet from the base of a tree, the sun shining on the tree and on the man, cast a 30-foot shadow for the tree. And we want to know how tall is the tree. So the idea here is that we have similar triangles. Okay. We've got the big triangle that's made by the tree and its shadow. And then kind of inside there, we've got a little triangle that's made by the man and his shadow. Little triangle and then the big triangle. So we can use the fact that these are similar triangles, figure out the side length we're looking for. We want to know how tall the tree is, so that'd be that left vertical side of the big triangle. Okay. So we want to set up a proportion. So one thing we could do, is we could look at the left side of the little triangle. That's the man. We know he's 6 feet tall. And that's going to be proportional to the left side of our big triangle, the height of the tree. So that's one thing we could set up. Right? There's several ways you can do these, but we could use the height of the man over the height of the tree. So we need some other numbers off our triangle to set up the proportion. So on this one, we don't have any numbers for the diagonal. Okay. We do have some numbers for the ground side, the bottom side though. We have to do a little bit of work though because we're missing one little piece, right? We know the bottom side of the big triangle is 30 feet. So I'm going to keep my big triangle numbers on the bottom. So the left side of the big triangle is the bottom on the left, and then the bottom side of the big triangle I'll put on the bottom to the right. And if we're going to do that, we want to compare that to the bottom side of our little triangle, which it doesn't give us, but we can figure it out. What's it going to be? 10, yeah, because we know the whole thing's 30. We know the man's 20 feet away from the tree. So 30 minus 20 gives us that we've got 10 feet between the man and the end of the shadow here. And so that part we can put in the top. Okay. And I'm going to take our little proportional equation and just recopy it on the next slide. So let's see, we got 6 over x is 10 over 30. They're all in feet, so I'm not going to write them down. Okay, so then when we have a proportional equation, what do we do? Cross multiply. So I like my x being on the left side, so I'm going to do x times 10 first. 10x. And then 6 times 30 is 180. Divide both sides by 10, so x is 18 feet. How tall is our tree? 18 feet. 18 feet tall. Questions on any part of that one? It did make it a little tricky. I was having to figure out that 10 feet down at the bottom. Yeah, but that was really the tricky part of that one, if there was one. So I know these can kind of seem overwhelming when you first look at them, but try not to look at everything all at once. Okay, try to break it down into little pieces. Okay? First thing we had to see is we had similar triangles there, and then we know we're going to have to match up some corresponding sides, so we can start working on that, and then we can worry about solving the equation. So you don't have to think about everything all at once. Okay, just take it a little step by step. All right. That's a similar triangle problem. There's not too many ways those can be thrown at you. Okay? That's the idea on those. Okay? All right, so the next little calculation we want to do is we want to be able to find the perimeter of a polygon. Okay? And perimeter is just the sum of the sides. I don't really like green, I don't think. I'm going back to red. Doing the sum of the side lengths. That's all there is to perimeter. Okay, so we're thinking like the distance around our shape. Okay. But since we're a polygon, it's not, we're having to walk down one side, walk down another side, walk down another side, and then we add all of those up. Okay. idea of perimeter. So let's look at a couple. These shapes are drawn on a grid, so kind of makes part of it a little easier for us. So each grid line's 1 unit is what we're calling it. Okay? Could be 1 foot, 1 mile, we don't know, just one, whatever unit. Okay? So on A, what would our perimeter be? How could we figure that out? We just start somewhere, and it doesn't matter which part you start on, and we just want to add up all the sides. On this one, all the sides are 1 unit, so we're really just counting how many we have. Let's say I'm gonna start at the top. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So my perimeter there is 12 units, whatever those units are. Okay. About on B, we're just counting grid lines. Okay, it's not each side's 1 on this one, but we're just counting grid lines. So I'm gonna start at the top again. This side's 1. This side's 1, 2, 3. The bottom side is 2. So the smallest out of here is 1, and then got 1 across the top, and then we got to go up 2 more. Okay, so if we add all those together, what do we get? 4, 6, 7, 8, 10. Might have just been easier just to count them as we went. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it does seem easier just counting as you go around. C is going to give us a problem trying to use our grid lines. What's the issue with C? We've got this diagonal on our triangle that doesn't match up to the grid, right? It cuts across some squares. We could estimate and get pretty close using the grid. We're not trying to estimate on this one. We're trying to get the exact answer. So the parts we can figure out, like this left side is 1 unit. This bottom is 2 units. And then we're trying to figure out what our weird sides are going to be. Anybody know anything we can use with a triangle to figure that side out? Not something we've talked about yet in here, but you might remember it from. We got 2 sides of a triangle looking for the long side. Yeah, Pythagorean theorem. Okay, so sorry, but here's where we run into Pythagorean theorem in this class. Okay, so Pythagorean theorem says a squared plus b squared is c squared. There are 2 short sides, 1 and 2. Those are going to be a and b. Figure out our other side that way. So here, I'm going to write it bigger. Here's our triangle again. We got 1, 2, and then looking for that one. So Pythagorean theorem says 1 squared plus 2 squared will give us our long side squared. So 1 squared is 1. 2 squared, 2 times 2 is 4. That's our long side squared. Gives us 5. But we don't want the long side squared, we just want the long side. So to get rid of, make c squared c, what do? We don't want c squared, we just want c. So we take the square root. Take the square root. So square root of c squared would be c, square root of 5 is just square root of 5. It's not a nice even number. Okay. So this side up here, we're not gonna get a pretty answer on this one. That's square root of 5, so we add all of our sides together, 1 plus 2 plus square root of 5. There's not a lot we can do with that. We can add the 1 and 2, but we get 3 plus square root of 5. So it's ugly, but it's the answer. If you wanted an approximation, and if you just wanted to be close enough, then you could figure out what square root of 5 is close to, and you get a decimal out of your calculator to approximate it, and then you could add that to 3, and you'd be close. But the exact answer is 3 plus square root of 5. There's Pythagorean theorem. Okay, we'll have to use it a little bit. We won't get super involved with it, but it does come up from time to time. Questions on that one? Okay, so just real quick on Pythagorean theorem, the side across from the right angle is always going to be the C, and then the other two are A and B. It doesn't matter which one you call A, which one you call B. Okay. All right, so that's perimeter. Just add up all the sides. It doesn't matter how many sides you have or anything like that. Just add them all up to get the perimeter. And the other thing we want to talk about is area. So area, we're talking about how many, so first of all, our units are going to be square units. And we're talking about how many square units it would take to like cover up the polygon. Okay? Or we're thinking about like how much space there is on the inside of our polygon. Remember, we're being flat, so it's just still a flat dimension, but it's squared. Okay? So area, we can, we're looking for the stuff on the inside, right? Like what's this dimension? How much space is covered up by our shape? So that's our area. And then here the red would be, if we added all the red sides up, that would be perimeter. So we're in the area as a two-dimensional thing. All right, so just quickly, we're going to kind of skim over some of the common area formulas. Okay. You might want to write these down for homework. Okay, but they'll be in the slides. The slides are on Canvas too, so you can get to them that way also. But you don't have to memorize these. Okay, since we've got so many, I will give you the different area formulas on the formula sheet and on test day. So, but you will need them for the assignment, though. Need them for the assignment. So, okay, so let's look at them. We'll start with the easy one. If we have a rectangle, our text gives us perimeter formulas as well. To me, those are not really useful. It's just easier just to remember, add up all the sides. Okay. But for our area, okay, for a rectangle, it's just length times the width. Okay. Times the width there. So this is the one we want. The perimeter, you can just add up all the sides. And you get, that's all that formula is saying. Okay. If we have a special rectangle where the sides are all the same length, what's that called? Square, yeah, it's called a square. Everybody knows what a square is, Mr. Stanley. So if we have a square, we can simplify our formula a little bit. But you really don't have to think about this one too much because you can still treat this like a rectangle. It is a rectangle, so you can still do length times width. But what this side is telling us is that if we know all the sides are the same, we can just do one side squared. Okay. So like here it would be s times s squared. That's the same thing as doing length times width. So, okay. And you might not think about it, but when we square a number, this is what we're doing, right? So it says that side's a S, this side's a S because it's a square. So what's our area? Our area is S squared, S times S. Okay? So that's why squaring a number means you multiply it by itself. Okay? There's a geometric idea behind that. We're finding the area inside of a square with side length S. Had a good geometry teacher, they linked all that together for you. They might not have. All right. Triangle's another big one we deal with a lot. So triangles can be turned different ways. Our formula says it's 1/2 times the base times the height. And so the base is always going to be whatever side's on the bottom, the way it's oriented. And the height needs to be a vertical line. So depending on how our triangle's oriented, like on this one, none of the sides of the triangle are straight up and down. So we're given a height like down through the middle of the triangle. If it's turned on its side, we could have my pen's sliding around my screen today. Could have a triangle turned like this. Then the bottom side's still the base, and that vertical side could be our height. That would be all right too. And our formula says it's base times the height, but we only want half of that. Anybody, have you ever thought about why that formula is the way it is? Why we have a half in our area formula for a triangle? Well, if we had a rectangle, I'm going to call my length B and my width H. Then my area of that rectangle would be B times H, length times width. But a triangle would only be half of a rectangle. So we would have to put a 1/2 in there. You get a half in there because the triangle is half of a rectangle. Don't have to know that for test or anything, but that's why. That's why we get a 1/2 in there. All right, so that's triangle. A couple of other ones. Okay. We can have a quadrilateral with slanted sides. That we call a parallelogram. So the idea with a parallelogram is like two sides are parallel with each other, and then the other two sides are parallel with each other. So a rectangle is a parallelogram, but a rectangle is a special parallelogram where the angles are 90 degrees. If you take a rectangle and you squish it a little bit, where it leans over, you end up with a parallelogram. And the idea here is it's the same as a rectangle, but instead of length and width, here they're calling it base and height because we do need a vertical line to be our height, like we did with the triangles. And if you think about taking that piece over on the left side, you think about chopping this piece off and sliding it over here, then we end up with a rectangle. The length's B, the height's H. So, yeah, base times height. Okay, so same idea. It's just squished. It's just squished over. Okay. And then one more. This formula is less useful in my opinion. But you can use it if you want to. Okay. It's the area of a trapezoid. So a trapezoid is four-sided. Right? We've got two sides that are parallel. So here on this picture, top and bottom are parallel. And then the right and left are not parallel. They would intersect. You can think about a trapezoid as being the shape we get when we take a triangle and we cut one of the points off. Right, so if we cut this piece off, get a trapezoid. So the formula here, the two parallel sides we call base 1 and base 2. It doesn't matter which one you call wedge. And then we have to have a vertical line for our height. And so then our formula says it's base 1 plus base 2 times the height, and we want half of that. Usually, why I say trapezoid formula is not as useful is you can split a trapezoid up into a rectangle and two triangles. Sometimes you can split it up into a rectangle and one triangle, because you can have a trapezoid that looks like this, where you only have one slanted side. And so then you could split it up into a rectangle and one triangle and just use those formulas and add the answers together. That's how the formula's doing. You can use the formula if you want to or not. Questions on any of the formulas? We're through them now, because that's all of them that we're going to be worried about. Okay on them? I'm not going over formulas. It's like really boring. Let's use some. So we got some shapes on our grid again. This time it tells us the units. It says assume the grid lines are each 1 foot. Okay. So on A, what shape's that? A rectangle, yeah. It's a rectangle. So we can just do length times width. So if I'm going to count the bottom side first. It doesn't matter which one you call length, which one you call width. It's 8. So 1, 2, 3, 4, 5, 6, 7, 8. Yep, so this one's 8. And then the height is 1, 2, 3, 4. So our area will be 8 times 4. So we get 32. And our units are feet. And since we're finding area, we're going to have square feet. So 32 square feet. And that's our area on this one. Okay. What about B? B is not one of our nice shapes we talked about. Any ideas what we could do? Yeah, that's a good idea. If you end up with some weird shape, okay, see if you can break it down into the simpler shapes that we know how to work with. So this one, you could split it right there and make a square and a rectangle, or you could split it right there and make a square and a rectangle. And either one of those is doable. I think I'm gonna split it across the top. So there, this square is 2 by 2. That area, 2 times 2 is going to be 4. Now my rectangle is 1, 2, 3 by 1, 2, 3, 4, 5. The area in my rectangle is going to be 15, length times width. So the total thing is going to be 19 square feet. Just add them together. And if you split it into little pieces, just add all the pieces together and you'll get the area. Okay. So that's a trick that's really useful. Okay. And then one more of these. Got a triangle, so here 1/2 base times height. So our vertical side, 1, 2, 3, 4, 5, that would be our H, our height. And then our base would be the bottom side. So 1, 2, 3, 4, 5, 6, 7, 8 would be our base. So we need 1/2 of 8 times 5. 8 times 5 is 40. So we get an area of 20 square feet. And it's fine, you can just do 1/2 times 8 times 5 in the calculator. There's nothing wrong with that. Questions on that one? Okay. All right, well, let's get another weird shape. Okay. So this one, we've got a kind of a aerial view of a floor, right overhead view of a floor. And we're going to paint this floor. And maybe it's concrete or something. We're going to paint the concrete. So we need to figure out how much area we're trying to cover. And then we'll figure out how much paint we need after that. Okay. So since it's a weird shape, we want to split it up. But you're not always given all the dimensions, so sometimes you just have to look at what the dimensions give you to figure out how we can split it up and figure out what we can do here. Anybody see a good way to split this up? See a side you can figure out? Or? I think maybe you can split it right there. So then I need to know what's this left side going to be. How can we figure it out? Somebody see? I know I got to have this part 7 feet. This part's 9 feet. So my left side's going to be both of those together. So this one's going to be 16 feet. And then what about top and bottom of my left piece there? Oh, we only need one of them. We just need top or bottom. They'll be the same. So let's see how we can get that. Plus the whole bottom, 40. So this is 40. This much of it's 28. So to get that other side, I can do 40 minus 28. Is that 12? Yeah. So this side's going to be 12 feet. Okay. So since these are both rectangles, this is my length and width for this rectangle. Okay. So I can do 16 times 12 for that one. Let me get a different color so we don't get as confused. So 16 times 12, what's that give us? It's 192 square feet. For my other rectangle, I'm going to use 9 and 28. And that's the length and width of that one. So 9 times 28 gives me 252 square feet. Then I'm going to add those together. Uh, 444 square feet. My whole thing. So this kind of thing comes up all the time, right? Because if you don't have a perfectly rectangular room in your house, okay, and maybe you're trying to figure out how much flooring to buy or something, okay, then that's what you have to do. You got to split it into rectangles. Usually you get to do your own measuring then, right? So you can pick which side you want to measure. But we've got a total of 444 square feet here. All right, B says if a gallon of paint will cover 350 square feet, how many gallons of paint are needed? real life here, so if we can only buy it in gallons, 350 square feet won't do it, right? That's not enough. We'll go 2 gallons, it'll cover 700 square feet, right? 350 by 2. So here we're not looking for a mathematical answer, we're looking for a practical answer. So how many gallons of paint will we have to cover? I mean, we'll have to buy 2, we got about 2. And we'll have some left over. Right? You can divide it, you could do 444 divided by 350 and get a 1 point something. But if we're actually going to the store, they're not gonna let us buy a point something can of paint usually. 2. Questions on that one? How we doing on time? All right, we'll stop there for today. We're getting pretty close. We'll finish this one up next time. If you didn't get on the sign-in sheet, I'll put it up front. And get on there. It's right there. Bring it. Thanks, sir.